Good day, guys. Today we are on our Unit 6, Transaction Management, Data Model, and Entity Relationship Diagram, also known as ERD. Now, for our essential question, this module aims to answer the following questions. How do we define a database transaction? How do we define a data model? How do the elements of a data model work? When and why did the different data models appear? What are business rules? As well as how do we create our own ERD, entity relationship diagram? For our intended learning outcomes, we will find the definition of a data model and the elements that make up a data model, the evolution and history of data models, business rules creation and the process of creating them, and Crossport diagrams. Now, before we begin our lecture, what I would like you to do is to read this particular page. It's entitled Before You Begin, Try to Do This Task Dash 6. Basically, we will try to make our own diagram, Chen and Crosspot, just by using the directions here. As you notice, for our Chen diagram, we have a rectangle which represents the entity or object. So inside the rectangle, you will place in capital letters the name of our object in singular form. We have a triangle which denotes the action from one object to another. We have a line which is used to indicate the movement of data from one object to another. It is connected from entity to action and from the action or the process to an entity or object. So basically, we are connecting two objects wherein one object performs an action on another object. And then for the Chen diagram, we have here for our Chen diagram, in order for us to denote the plurality or the number of entities or objects interacting, we use the symbol zeros if the object is none or the count is zero, one if the object is only one, M it indicates that the object count is many, and we also use the symbol N for many when we have already used M in our line. So for example, M N. That indicates that for our first object is many and we are connecting it to another object that is also many. Now, to give you an example, we have here two sample diagrams, which is about a farmer and his crops. Okay. Now, in our first rule, our first description, a farmer grows many crops. Now, as I have said, your object, which is your noun, is or should be placed in a rectangle, in a singular form, and in all capital letters. So we have here a farmer, which is one farmer, okay, and then many crops, so crop, many crop. So our action is indicated inside our diamond. So one farmer grows many crops. Okay, that is our first example. For our second example, we have many crop are bought by many trader. So many crop are bought by many trader. Notice that as I have said earlier, if you have already used M as a symbol for many, and you are connecting to another object which is also many, Instead of using M again, you will use the letter N. Okay. Now, for our crosspot diagram, we have the following symbols. Instead of using a rectangle and a crosspot, we use a square wherein the object name is stated above the square and it is separated by a line. Okay? If you are familiar with class diagram, or if you have already tackled class diagram, um, the rectangle used in a class diagram is the same as that used in a crosspot diagram. So basically, the name should be in capital letter, should be in singular form. Okay. Now, for our action, it is denoted by a line wherein the action should be located on top of the line if it is horizontal, and usually it is found on the right if the line is vertical. Okay. For our symbols, we will use the following sample symbols. Now, why is a crosspot diagram called a crosspot diagram? The main reason for that, or one of the main reason for that, is that the symbol for one or many, looks like the foot of a crow. Okay, as you notice, this symbol, one, is indicated by a vertical line, and many is indicated by this three line. So one or many. Okay. Now, what are the symbols used for a crow's foot? We have here, first example is zero or many. Sorry, zero or one. Okay, so one is indicated by the vertical line. We have here one. Okay, although there are two lines, that symbolizes that the object is only one. And then we have here one or many. Okay, one or many. Now, if you are going to use this in an actual diagram, you will come up with something like this. So these are the objects, this is the action, and then this is the relationship. So we have one or many object, action, one or many object. To give you an example, we will go back to the two samples we have earlier for Chen's diagram. So we have here a farmer grows many crops. So as I have said, there's only one farmer. So one farmer grows one or many crop. Okay. So notice that for the symbol for the symbol many, we always use one or many. Okay, there is no symbol that is only three lines. We always have to have two symbols for each plurality. By the way, going back, we can also have a relationship of zero or many. Basically, instead of putting one vertical line, you replace it with circular line, and then we put in the symbol for many. Okay, and next example, many crop are bought by many trader. So we have here one, so this actually should be farmer. So one or many crop, okay, it's this typographical error. I will correct this later on. One or many crop are bought by one or many, this should be trader. Okay. Now, I have given here two sample situations. What I want you to do is to provide the Chen and the Crossport diagram for the two samples. And then after creating the Chen and the Crossport diagram, try to do your best to connect the individual diagrams. So basically we have three diagrams, and then we will try to connect them to each other. But we have to make sure that no object or entity is repeated. Basically, all the objects will have to only appear once. Okay, take note that you can draw the lines vertically or horizontally in order for you to denote relationship. You could even do uh, vertical, horizontal, and then vertical line if you are to connect one object to another. But a diagonal line is not allowed. Okay, only straight lines. It could either be um, vertical, horizontal, or vertical, horizontal, vertical, or it could be a horizontal, vertical, horizontal line. Okay, but try to make your diagram as um, simple and as straight as possible. Okay, now let's go to our actual lecture proper. So for our Unit 6 lecture, so first topic is about transaction management. So when several users access or modify a database concurrently, the DBMS must order their request carefully to avoid conflicts. A transaction is any one execution of a user program in a DBMS. Executing the same program several times will generate several transactions. This is the basic unit of change as seen by the DBMS. Partial transactions are not allowed, and the effect of a group of transactions is equivalent to some serial execution of all transactions. So basically, when you say transaction, as we have, if you will remember, as we have discussed in our past few lectures, basically a transaction consists of one or more several operation. If one operation fails, then that transaction will not push through. But if all of the operation succeeds, then the transaction will push through. Although they are different operation, they are treated as one transaction. Okay. So if you may remember the example we have when person A deposits money to person B, the starting balance of person A, for example, is $200 and person B has $0. So when person A deposits $100 to person B, okay, at the end of the transaction, the total amount should still be $200 and the amount given to person A is 100 and person B is 100. Okay, so that is transaction. Now, data modeling. When we say data model, it is basically a relatively simple representation, usually graphical, of more complex real-world data structure. In general terms, a model is an abstraction of a more complex real-world object or event. Its main function is to help you understand the complexities of the real-world environment. Within the database environment, a data model represents the data structure and their characteristics, relations, constraints, transformations, and other constructs to support a specific problem domain. An implementation-ready data model should contain at least the following components: description of the data structure, a set of enforceable rules, and a data manipulation methodology. A description of the data structure will store the end user data, while the enforceable rules will guarantee the integrity of the data, while the data manipulation methodology should support real world data transformation. What are the building blocks of a data model? It should have an entity. Okay. An entity is anything about which data are to be collected and stored. So it could be a person, a place, a thing, or an event. Okay, it represents a particular type of object in the real world. It's unique and distinct. For example, a customer entity would have many distinguishable customer occurrences such as John Smith, Pedro Dinamita, etc. They may be physical objects such as customer products, but they can also be abstractions such as flight routes or musical concert. Now, we also have attributes, which are characteristic of an entity. For example, a customer entity would be described by attributes such as customer last name, first name, phone number, address, and credit limit. Attributes are the equivalent of fields or columns in file systems. And lastly, we have relationship. It describes an association among entities. For example, a relationship exists between customer and agents that can be described as follows. An agent can serve many customers. Each customer may be served by one agent. Data models use three types of relationship, which is usually these are the three types, but as we have as you have seen in our examples earlier, you could also have other relationship, including zero or none. Okay, we have here sample shorthand notations that database designer use. One colon M, which signifies one is to many, or could be one dot dot asterisk, wherein asterisk represents many. Okay, we could also have one colon N or asterisk dot dot asterisk and one colon one or one dot dot one. Okay, examples of relationship. We have one to many relationship. For example, a painter paints many paintings, but each one of them is painted by only one painter. A painter paints painting signifies as one is to many. Many to many relationship. An employee may learn many job skills, and each job skill may be learned by many employees. Database designer can label the relationship employee learns skill or many employee learns many skill. We also have one-to-one. A retail company's management structure may require that each of its store be managed by a single employee. In turn, each store manager, who is also an employee, manages only a single store. Employee manages store. So one is to one. Constraint is a restriction placed on the data. They are important because they help in ensuring data integrity and they are normally expressed in the form of rules. For example, an employee's salary must have values that are between 6,000 and 350,000. Should not be lower than 6,000. Okay, it should not be higher than 350,000. A student's GWA must be between 1.0 and 2.0. So those are constraints, a restriction placed on the data. Business rule, on the other hand, is a brief, precise, and unambiguous description of a policy, procedure, or principle within an organization. They apply to any organization, large or small, whether they be a business, government unit, religious group, a research laboratory, etc., etc. Properly written business rules are used to define entities, attributes, relationship, and constraint. So we use business rules for the following reasons. Standardize the company's view of data. Serves as a communication tool between users and designer. It allows the designer to understand the nature, role, and scope of the data. It allows the designer to understand business processes, and it allows the designer to develop appropriate relationship participation rules and constraints, creating an accurate data model. For example, consider a company that sells books online. So business rules defines the discount which you can apply in each individual case and also what the minimum threshold is to offer free shipping to customers. For example, a business rule will also establish that you can only send a purchase after recording that particular customer's payment. In another case, consider a software as a service or SaaS that works from recurring sales. The company has been experiencing problems with defaulter clients. What do you do if you don't receive a payment within the agreed upon time limit? The company that makes software as service available can decide to cut the software supply based on a deadline established through a business rule. Thus, or sorry, that is, it may decide to cancel the subscription of a client who fails to make payment for 2 consecutive months, for example. You should realize that executing these types of processes is fundamental. It is not enough to just know how to analyze and define the established rule if you can put them into practice. Imagine in the above situations how these processes would occur if all of the guidelines didn't exist or depended only on manual tasks. Have you thought about having to decide case by case what discount to give a retailer or whether to cancel the accounts of a delinquent clients? Certainly, your business would lose productivity and mistakes could happen. So basically, guys, when we say business rule, they are the set of rules that define the entire operation of an organization. So from conditions such as setting the discount for a particular customer, what should be the condition in order for a customer to have free shipping, what would be the condition if a customer has not paid their balance for the past 2 months, etc., etc. Those are business rules. Okay, so how did data models evolve? So looking at figure 20, you can see here from the first generation up to the current generation, which is the emerging models, we can see the different evolutions of the different database model, including the examples. Now, among these data models, we have the hierarchical and network models, which appeared during the second generation of our data model. The hierarchical data model was developed in the 1960s to manage large amount of data for complex manufacturing projects such as the Apollo rocket that landed on the moon in 1969. Its basic logical structure is represented by an upside-down tree. The hierarchical structure contains level of four segments. A segment is the equivalent of a file system's record type. Within the hierarchy, a higher level is perceived as the parent of a segment directly beneath it, which is called the child. The hierarchical model depicts a set of one-to-many relationship between a parent and its child segment. Each parent can have many children, but each child has only one parent. In the hierarchical model, a hierarchical relation is formed by a collection of relations and forms a tree-like structure. The relationship can be defined in the form of a parent-child type. One of the most popular and first example of hierarchical model is the IMS, or Information Management System, developed by IBM. So we have here an example under figure 21. The hierarchy shows an employee can be an intern, a contract, or a full-time employee. Sub-levels show that full-time employee can be hired as a writer, senior writer, or an editor. The advantages are the design of the hierarchical model is simple, provides data integrity since it is based on a parent-child relationship. Data sharing is feasible since the data is stored in a single database. Even for large volume of data, this model works perfectly. While the disadvantages are the implementation is complex, the model has to deal with anomalies like insert, update, and delete. Maintenance is difficult to provide because changes done in the database may want you to do changes in the entire database structure. The network model, on the other hand, was created to represent complex data relationship more effectively than the hierarchical model to improve database performance and impose a database standard. In the network model, the user perceives the network database as a collection of records in a one-to-many relationship. However, unlike the hierarchical network, the network model allows a record to have more than one parent. So the concepts that were defined during this time are schema, which is conceptual organization of the entire database, viewed by the database administrator. You have the subschema, which defines a portion of the database seen by the application programs that produces the desired information from the data within the database. We also have the ML or data management language or data manipulation language, which defines an environment in which data can be managed and to work with the data in the database. And we have data definition language or DDL, which enables the database administrator to define the schema components. The hierarchical model creates hierarchical tree with parent-child relationship, whereas the network model has graphs and links. The relationship can be defined in the form of links and it handles many-to-many relation. This itself states that a record can have more than one parent. So for example, we can see here under figure 21b. The advantages are easy to design, can handle one is to many, or many is to many relationship. It isolates the program from other details, and it is based on standards and conventions. While the disadvantages are pointers bring complexity since the records are based on pointers and graphs. Changes in the database isn't easy, making it hard to achieve structural independence. The relational model, introduced in 1970 by E.F. Codd of IBM in his landmark paper, A Relational Model of Data for Large Shared Data Banks. The relational model represented a breakthrough for both users and designer. To use an analogy, the relational model produced an automatic transmission database to replace the standard transmission databases that preceded it. The relational model foundation is a mathematical concept known as a relation. To avoid the complexity of an abstract mathematical theory, you can think of a relation, or sometimes called a table, as a matrix composed of intersecting rows and columns. Each row in a relation is called a tuple. Each column represents an attribute. The relational model also describes a precise set of data manipulation constructs based on advanced mathematical concept. Arguably, the most important advantage of relational database management system is the ability to hide complexities of the relational model from the user. It manages all the physical details while the user sees the relational database as a collection of tables in which data are stored. So we use a relational diagram, which is a representation of the database entities, or the relational database entities, and the attributes within those entities and the relationship between those entities. End users perspective SQL-based relational database application are the following. We have end user interface, allowing end user to interact with the data by auto-generating SQL code. We have a collection of tables stored in the database. All data are perceived to be stored in tables. They present the data to the end user in a way that is easy to understand. Each table is independent, and rows in different tables are related by common values in common attributes. And lastly, we have an SQL engine which executes all queries or data requests. The SQL engine is part of the database management system software. So a relational model groups data into one or more tables. These tables are related to each other using common records. The data is represented in the form of rows and columns or tables. So we have an example here wherein we have two tables, the employee and the department. So the employee has a relationship with the department, the sense that each employee has a different department ID, which we could connect to the department table. So the primary key is the department ID found in the table department, whereas the foreign key is the department ID found in the employee table. Why is that? Because the department ID is a main column for table department, whereas the department ID for employee is just a means for signifying or connecting the relationship between the two tables. What are the advantages? They do not have any issues that we saw in the previous two models. Update, insert, and delete anomalies have nothing to do in this model, so they do not exist in this model. Changes in the database do not require you to affect the complete database. The implementation of this model is easy, and to maintain this type of model is not a tiresome task. While the disadvantages are database inefficiencies hide and arise when the model has large volumes of data, and the overheads of using relational data model come with the cost of using powerful hardware and devices. Now, this database model that we will tackle called NoSQL is a form that is currently popular today to manage large sets of data. Um, More specifically, it is used by Amazon, by Facebook, in order for them to get and process tons and tons of data. Around 2008, triggered by Facebook's open source versions of Hive and Cassandra, the NoSQL counter revolution started. This space gets all of the attention today. 2008 was indeed the turning point. This can also be seen in the report of the very influential Summit of Database researchers which have met in 1989, 1990, 95, 96, 98, 03, 08, and 2013. In 2008, big data was the number one factor for a sense of change. So where do we go now? How to balance the what and the how in light of no SQL and the all new technologies. While the modern development platforms use schema-free or semi-structured approaches, also under the umbrella of NoSQL. Model as you go is a common theme, while data modelers and data governors are seen as relics from the past. Surveys confirms this. Modeling for NoSQL is very often performed by the developer on the fly. So basically, NoSQL uses a schema-free or semi-structured approach. Basically, unlike relational database wherein um, the data are arranged in a particular order or set based on the column, NoSQL does not need to do that. However, this that does not mean that a relational model is obsolete or is not used, because let's say for example, if we are to process a fixed set of data in a particular table, it is still more reliable and more efficient to use a relational model than using a NoSQL model. Why? Because a NoSQL model can sometimes bring about problems with uniformity. For example, in one of your row of data, you have eight columns. But in a NoSQL model, sometimes the second and the third data can have only three columns, one column, okay, and then followed by another record which contains a different number of columns. So basically, NoSQL is not fixed because it does not have particular structure. However, it is useful for processing large sets of data, okay, which is usually for data retrieval. But if there is consistent updates or modifications of data, relational data model is still the way to go. Entity relationship model or ER, ER model. A graphical tool in which entities and the relationships are pictured. First introduced in 1976, they are normally presented in an ERD or entity relationship diagram, which uses graphical representations to model database components. They have two components, namely the entity and the relationship. So entity is anything about which data are to be collected and stored, okay, usually represented by a rectangle or by a square, also known as an entity box. The name of the entity is a noun, usually written in capital letters and in single or singular form. Whereas relationship describes associations between data. So it can be in the form one to many to many, or one to one, or sometimes they also use zero or one, or zero or many. We have two major types of entity relationship model. First one is the Chen notation, based on Peter Chen's landmark paper. All the connections are written next to each entity box, represented by relationship using a diamond connected to the related entities. Okay. We also have the Crossport notation, so derived from the three-pronged symbol used to represent the many side of the relationship. For example, 1 is represented by a short line segment and M is represented by a three-prong or crow's foot. The crow's foot notation was invented by Gordon Everest, which originally used the term invented arrow, but now just calls it a fork. For cardinality, a fork or crow's foot intuitively indicates many or by its many toes. So we have here sample between a Chen and Crossport notation. As you notice, we have discussed this earlier. For the Chen notation, objects or entities are represented by a rectangle. For the Crossport, it is usually a square with a line separating the object name. Okay. For the action, Chen notation uses diamond, while Crossport basically just uses a line, and that line is where the action is written, either on top or on the side, usually on the right side. For the plurality or for the count, the notation uses 0, 1, M, or N, whereas Crossport uses line symbols, 1 for singularity, circle is for 0, three lines or a fork for many. Okay. Crossport symbol for 0 or none is circle. So 0 or many, or 0 to many, or 0 to 1, 0 or 1. So those are the symbols used for our Chen and Crossport notation. Components used in the creation of an ERD. So as I've said, we have here an entity. Take note, in this example, we are using an entity wherein the entity or object name is separated by a line. When creating class or class diagram, we could also include the attributes on the bottom part after the line. So this place usually houses the attributes as well as the particular data type of those attributes. A relationship is signified by a line, okay, while the cardinality and modality, as I have said, is signified by this one is for the crow's foot. Okay, I will not repeat it anymore. So these are example. So for example, one student fills one seat. Okay, one instructor teaches one or many course. Take note, the symbol is M, but how come we still use one or many? Okay, it depends on the particular notation that you are using. Always remember that crossport needs to have two figures or lines drawn um, to our modality, unlike Chen, which could use only one particular symbol. We have here many, one or many student takes one or many course. As notice, it is more advisable to use N instead of M if you are using a many to many relationship. Then we have here one professor teaches zero or many section. Okay. Where in ancient notation there is only one or many. So if we are to connect all of the given diagram using crow's foot, we can see here that the objects or the entities are not repeated. Okay. We have a single student, single instructor, course section, professor, and team. Okay. Take note that we could angle the line if we are to connect them from one entity or one object to another. It's not required to have a straight line. Also in this example, we have written the columns or attributes of that particular object. So for student, for example, we have student ID, student name, and student address. We have here an example. Okay. So using Crossport, this will be the result. Take note, usually when we are creating a diagram, Chen or Crossport notation, the description that is given are actually business rules already. So basically, from the business rules, we could actually create a particular notation. Okay, if that particular business rule provides at least two entities and force of action. Okay, so take note of that. Business rules must come first, and they are able to provide the input for our notation or our diagram. Okay, so if you notice, some lines interact with other objects more than once. Okay, you can see. But basically, this can all be separated into individual diagrams or individual notations. Okay? Basically, one particular action is one particular business rule. We just plotted them in one diagram. Okay? For example, doctor one doctor is scheduled for zero or many appointment. Okay? One appointment generates one bill. One bill, okay, pays zero or many payment. Zero or many payment makes or is made by one patient. One or many patient is insured by zero or one insurance company. And one insurance company is made makes sorry. So basically if we are to invert this line, one insurance company makes one or many payment. Okay, so we are not following this one because this one came from this entity. If we are to follow that, it could be one or many payment is made by one insurance company. So it could go in reverse also. Intersection entities. Intersection entities which are used in the resolution of many-to-many relationship. This resolution is done in order to store additional information which doesn't fit into the attribute list of either entity in the many-to-many relationship. Okay. So basically, intersection entities are like this. So that is the symbol for intersection entities. We will not be using this particular type of entity. However, I have included this in order for us to know that there is also this type of entity. So we will look on the example. A course can have many sections and a section can have many courses. If we want to know how many students are registered in a particular class, we cannot store the information on either entity. We could store the total number of students registered in all sections of a particular course in the course entity. Okay. 300 students are registered in CS270, all sections included. We could store the total number of students registered in all courses with a particular section number. 25,000 students are registered in the section numbered 0002. If we want more practical information, such as how many students are registered, we need another entity in which to store the information. So we create an intersection entity and it is placed between related entities with additional attributes. The MM relationship becomes two, one is a many relationship. So from here, basically to shorten the explanation about intersection entities, basically intersection entities are entities or objects that are included to the design of our diagram in order to accommodate or facilitate the need for other entities. Usually, later on, you will learn the concept of database normalization, wherein one table is cut or split into two or more tables. This is done in order for us to have an easier access, easier management of data. That concept applies to intersection entities. Notice from our figure 23, which is our table for student, course, instructor, seat, section, and professor, when we introduce an intersection entity, in this case, the entity class, okay, we split, we split up the need to directly access the course to the section. Now, in order for us to have a separate link of data from the course to the class and the class to the section, we introduce the class entity. Now, we will not be dwelling or using many examples of this one. I just introduced them to you so that you have concept of what an intersection entity is, but we will not be diving deeper into this one. We will be using more or less the ordinary forms of Chen and Crossport, so you do not need to worry. However, take note that this type of entities exist. Okay. Also, aside from intersection entity, we also have independent entities. Basically, entities are those which can exist without another entity. For example, student, seat, instructor are examples of independent entity. The student, seat, instructor, okay, they are independent entity. They can exist without the need for other particular entities. Of course, aside from course for the instructor and student, and the student for the seat. We also have dependent entities which, according to the word, rely upon the existence of other entities. Some of their attributes are taken from the identifiers in the entities upon which they depend. Class is an example of dependent entity. It relies upon course and section and gets two of its attributes from their identifier. To convert the previous crowsfoot diagram to Chen notation, we just have to change the lines representing the cardinality and modality. So we have three types of additional entities. We have intersection entities, independent and dependent entities. So just take note of their meaning. Basically, with regards to entity relationship diagram, our focus is to create diagrams and not to dwell on the different uh, descriptions or the different classifications of those entities used. Okay, now um, let me show you an example of how we can convert one diagram to another. So in our figure 23, we use a crow's foot. Okay, from this diagram, if we are to convert it into a Venn diagram, okay, this will be the result. Notice that in some instances, with regards to the modality, okay, specifically the relationship of one is to many, in order for us to denote that particular modality, okay, do not forget to include the colon symbol. So from this one, so one is to many, it becomes 1 is to n. Okay. And then also from this symbol, 1 is to many, 1 is to many. Okay. 1 is to many, 1 is to many. And then we have here 0 or many. Then we have here 0 or many. Okay. So that is how you would convert from crow's foot to Chen and Chen to Crossport. So we have other examples here. Okay. Doctor, one doctor is scheduled for zero or many appointment. And as I have said, you could do the relation, you could read the action in reverse if you want to. So if we are to read this in reverse, one appointment is generated by one bill, okay, or one bill generates one appointment, and then one bill, okay, pays zero or many payment. And zero or many payment makes or is made by one patient. One or many payment is made by one insurance company, and one or many patient is insured by zero or one insurance company. Now this is for the class example. So basically we just change um, the symbols for that. Notice also that for your entity we use Chen, right? For Chen, okay, you could also remove the different columns or description if you want, and then remove the line. Basically just put their student if you want to. There are many representations of diagrams, okay, but we are sticking with the ones that will be easier for you. So in this example, we do not need to fill up the different description or columns in that particular entity. Okay, so for this one, there is no need. However, you just have to remember that if you are using Chen, okay, remember that you need a rectangle with an entity inside. There's no line, so remove the line. Okay, if you want to make it simple. Then we also use symbols, 1 or M or 0 or N, and then we use a diamond for the action. For the cruise foot, always remember that the entity should have a name and then separated by a line. And then the action is placed on top or on the side of the line. And then our plurality is symbolized by, okay, either line, a fork, or a circle. And then always remember that when using Crossport, we are always having two plurality. Okay, always remember these are two, except for the one or one. Basically, that's just one. But for other examples, one or many, zero or many, one or many, one or many. We also have zero or one. Okay, always remember that. For any clarifications, you just need to contact me via our Discord server if you want other examples. But try to break down this diagram. The easiest thing that you could do if you want to deconstruct this is you could write the business rules. Let's say, for example, one student takes one or many student takes one or many course. You could write that in a business rule as many student takes many course. Or if you are to follow the actual Crossport or Chen notation, one or many student takes one or many course. One student fills one seat. Okay? And then from that business rule, you could try to rewrite it again and then try to see if you have come up with the same diagram. So that is how you can practice creating your diagram. You can start with just a piece of paper so that it will be easier to you. Then later on, you could use Microsoft Word and then use the symbols and the text box if you want. Okay, so that would be it. Just don't forget, guys, to answer and upload your assignments for our before you begin to try this task. Okay, and also for our laboratory, which I have given here a set of problems. Okay, so I'll be seeing you again on Unit 7 lecture. Thank you.